We are excited to have such an enthusiastic and diverse group of participants gathered here to explore and discuss the latest advancement in composite materials. To ensure a seamless experience during the session, we kindly request you to cooperate with the following guidelines. Please keep your microphone muted throughout the presentation to avoid any interruption. We encourage you to actively listen to the session and note down the questions that you may have. If you have any query during the presentation, please type your questions in the chat box and speaker will address them during the question and answer session. Let us all maintain the professional decorum by refraining from interrupting the speaker during their talk. Thank you for your attention and cooperation. We are looking forward to an inspiring and thoughtful session. Now, it's my distinct honor to introduce our esteemed keynote speaker, Dr. Prashantha Kalappa, a distinguished academician and researcher, serves as a professor and dean of research and national science at Adichunchanagiri University with a profound experience in the realm of advanced smart polymer, biopolymers, biomaterial, 3D printing, and bioprinting, as well as microplastic and environmental studies. His academic journey is an adornment with remarkable achievement, including the award Doctor of Science degree conferred upon him by the University of Lille, France, in recognition of his contribution to the domain of advanced polymer material. Notably, his scholarly pulse shows acknowledgement globally, earning him a position in Elsewhere esteemed list of top 2% of scientists in the world for both 2021 and 2022.
Online.
He is elected Fellow of Royal Society of Chemistry, UK. Dr. Prashantha serves as an associate editor for Polymer and Polymer Composite and holds the esteemed position of International Advisory Board member for Express Polymer Letters. He also serves as a reviewer for numerous prestigious international journals. The professor has published 120 research papers in a peer-reviewed international journal with over 4,000 citations with an H-index of 31. Prior to his tenure in India, he served as a position of professor at the Polymers and Composite Technology and Mechanical Engineering Department at Institute of Mines Telecom, Lille, Dubai, France. During his tenure, he also assumed a pivotal role of Dean for International Scientific Affairs, overseeing the national and regional project, industry collaboration, and European initiative such as Horizon 2020. He also successfully supervised the research endeavors of 5 PhD candidates and currently guiding 8 PhD students, nurturing the next generation of scientific talent. Dr. Prashantha has delivered keynote and invited lectures as esteemed international conference, fostering the collaboration with leading industry and academia worldwide. With more than 22 years of experience, he continued to amplify excellence in research, education, and global collaboration. The keynote talk title is Biodegradable, Non-Composite, and 3D Printing, Smart Polymer, Innovation in Energy Harvesting and Next Generation Sensing Technology. Today, he will be delivering insight to this the topic as a biodegradable thing. And please join me by giving a warm welcome to Prashantha Kalappa. Over to you, sir.
Okay, thank you, Dr. Uma Narayanan, for the nice introduction. At the outset, I would like to thank Dr. Vijay Srivastava, whom I met in France. He visited our institution while I was in France in 2010. And I think, thank you very much for the opportunity, Professor Vijay Srivastava, sir. He was at the time, he was at IIT BHU. And I also would like to thank Dr. Praveen KM for overseeing and coordinating with me for this conference. And Jai Shri Gurudev, and today I will be talking on biodegradable polymer nanocomposites and metal oxide nanocomposites. I will keep 3D printing away from today's presentation, and I will be talking on how we can use biodegradable nanocomposites for innovation in energy harvesting and also metal oxide nanocomposites for electrochemical sensing technology. My first part of the talk focuses on the biodegradable polymer nanocomposites for energy harvesting technology. So energy harvesting refers to, as you know, capturing of energy as well as storing of a small amount of energy at ambient energy from the environment to power low energy devices like sensors, actuators, and so on. This technology is especially useful for application where traditional power sources such as batteries are impractical because the size and everything is huge. And they are undesirable due to maintenance, size, and environmental concern, so that we can power the energy we can generate the energy by external means. So you can convert mechanical energy into electrical, thermal energy, solar, bioenergy, electromagnetic energy, and wind power to energy source. This is a very well-known concept. And source and types of nano generators. So, nano generators are generators where we can generate the energy in terms of nanoscale. So source can be mechanical, thermal, chemical, or radiant energy source. And we can convert the methods such as electromagnetic energy harvesting, piezoelectric energy harvesting, triboelectric, electrostatic energy harvesting. As you know, electromagnetic energy harvesting requires response to electromagnetic radiation. Piezoelectric energy harvesting requires material should be piezoelectric material. Triboelectric is like, you need to tap or apply some tribo type of forces. And electrostatic, you all know. So applications is very vast. We have wireless sensor technologies, renewable energy sources, detectors, vehicles, transducers, human motion, wearables, microwave antennas, and so on. So these kind of materials finds very good applications in various fields. So what are nanogenerators? A subclass of energy harvesting devices that leverage nanoscale materials and phenomenon to convert mechanical or other forms of energy into electrical energy, which is very, very small. And source is basically mechanical energy as well as environmental energy. So you can use this energy in biomedical devices, environmental sensing, powering small electronic gadgets, and energy harvesting from irregular mechanical motion. Therefore, you can harvest the wastage, you can harvest the energy which is going to be waste, and you can convert that energy into useful for the useful applications. Principle is very simple. It can be triboelectric, piezoelectric, or pyroelectric. In our work, we focus on triboelectric nanogenerators. So what are triboelectric nanogenerators? Based on the triboelectric effect and electrostatic induction, they convert mechanical energy into electrical energy through contact and separation. So I will show you the mechanism at the end of my presentation. And these materials can be used in wearable devices, cell-powered sensors, energy harvesting from vibrations, and underwater robotics. Piezoelectric means obviously you are going to use piezoelectric material where you can highlight the piezoelectric effect into mechanical stress, which is applied to piezoelectric material, and that generates the electrical change. So this can also be used in biomedical device, mechanical energy harvesting, flexible, and so on. So only thing is in triboelectric material, we are going to force the material. We are going to subject the material under triboelectric forces. In piezoelectric materials, we are going to have the piezoelectricity within the system. So that is a major difference between tanks and panks. So pyroelectric means harvesting energy from a temperature fluctuation by utilizing pyroelectric material. So the difference in temperature also gives some amount of energy that can also be harvested. Thermoelectric, which is similar to pyroelectric, and electrochemical nanogenerators harvest energy through electrochemical reaction because it is simple electrochemistry where anode and cathode, the difference in the potential leads to some amount of energy that is in terms of nano energy. But of course, these materials finds very less application because of the fluid nature of the chemical reaction. So here is the mechanism of tank. So when you have plus, you have two types of material. The triboelectric nanogenerator is an energy harvesting device that converts mechanical energy into electricity using triboelectric effect, where it was first demonstrated by Zhang Wang groups from the Georgia Institute of Technology in 2012. Since then, there are many groups working on this to improvise the material properties and also to find various applications. Yeah, the chemical bond is formed between some parts of the two surfaces when two materials come in contact. That is the adhesion. The adhesion material become electrically charged after it contacts. When it contacts, and material through friction. It can be a friction or a triboelectric like this. So when these materials come in contact and then separate due to external force like motion or vibration, electric charges are generated on their surfaces, creating an electric potential difference that can be harnessed as power. The charges move from one material through the other to equalize their electrochemical potential. You can see here there's a when it is pressed and when it is released. So when it is released, when it is releasing, so then the amount of energy which transforms and that can be stored. Again, this process can be pressing, releasing, can be repeated several times so that the energy can be harvested. Because here you see here the sustainability. The material can be a sustainable material and which is very strong and which can withstand any number of tappings or anything. So there are many types of vertical contact separation and then lateral slide movement. Everything is, it is similar, what I can say. Vertical separation mode, material contact and separate vertically, generating electricity through charge and induced potential difference. And lateral sliding is a dielectric motion slide laterally, producing alternating current. And single electrode mode is a single dielectric material. And in case of freestanding triboelectricity is, a free-moving dielectric alters the electrostatic balance between stationary electrodes, which are ideal for guided motion separate. And, depending on the energy which you can find, you can have vertical contact, lateral sliding, single electrode motion, or freestanding, depending on where exactly you will find. So now we are focusing only on vertical contact separation because it's very easy to do. So there are advantages. They're like a high output voltage, wide material compatibility. You can use any kind of material, which should be, positive or negative. So there are some material which are positive.
Professor,
Yes.
I think your voice is little feeble now.
Okay. Can you hear me now?
Yeah, I can hear you, but initially it was very good, but now it is
Now it is very slow. Okay. Okay. Yeah, I will modulate. Okay, sorry. Then they find very wide material compatibility. The cost is very, very low because, if you consider the ceramics, the density is very high and the polymer density is very low. And the efficient at low frequency, you can give any kind of frequency because of the flexibility of the material, which can be scalable, versatile, which is environmentally adaptive and lightweight. As I told you, density of the polymer material, which are very light, and materials can be eco-friendly. So this is what we are focusing. Today, we are focusing on biodegradable materials, which aligns with sustainability goals to reduce the accumulation of plastics in the environment. So see here, what are the advantages of tank? Tank gives high voltage and low current, high efficiency at low frequency, low cost and lightweight, and it has diverse material choice because, in the literature, we can see a lot of polymers which are already being reported. So there is a lot of choice to select what kind of material you want to use. But at the same time, which have some limitations, such as protection of tank surface from the environment is very difficult. Because, all the tank triboelectric nano generators requires, surface texture. Whatever the potential you generate or whatever the electricity you generate, which is directly proportional to the texture of the materials on the surface. So it is very difficult to maintain the structure because of the tribo effect. Tank does not have long durability and stability. This is another thing we are finding because after 300 cycle or 400 cycle, you try to reduce the tank capacity. And precautions should be taken when tank is combined with other energy harvesting devices. So what are the challenges? There are some challenges. Selection of triboelectric material because it should be, you have to select both positive as well as negative, and reducing the accumulation of plastic waste because just because plastics are available and you cannot use it because it is hazardous to environmental. And you can have the tank, by 3D printing technology and increase the stability and durability, enhancing dielectric properties, surface modification by lithography, increasing the contact surface area and structure modification, which are all very, very difficult, are very, the challenges which are encountered during the fabrication of tank devices. So you see here, what is the research gap and what we have done in our work. So there is extensive literature reported on the polymeric material using metal oxides, but there are some metal oxides which are very effective, which are semiconducting nature: aluminum, zinc, calcium chloride, lithium, LiMNO3, graphene oxide, and so on, using petro-based polymers. So there are very limited exploration of bio-based polymers such as polylactic acid, polybutylene adipate, terephthalate for triboelectric application. So the present work focuses on the usage of these biodegradable polymers such as polylactic acid or PBAT to fabricate tank devices. So why nanomaterials? Because you all know nanomaterials are versatile, which brings very high surface area. And why? So while we have very high surface area, of course, it gives a lot of advantages: multifunctionality, which can be conducting, mechanically strong, thermally stable, and its creep and fatigue behavior is very strong. So see here, as I told you before, the mechanical properties of the nanomaterials are very high. Therefore, when you reinforce the mechanical nanomaterials, you can have good mechanical properties: electrical, magnetic, optical, thermal, and chemical resistance. That is the versatility of nanomaterials when you use them in polymer matrix. So what are polymer nanocomposites? You must be aware of it. If you reinforce any nanomaterial, which is at least in one dimension, is in nanoscale in the polymer matrix, which can be called as polymer nanocomposite. But in terms of time, what is more important is the interaction zone. So what is marked in the red zone is very, very important, because that's the way where the electricity or the current generates. The texture is directly related to the interface of the material. So why you are using biodegradable material? Because we don't want to harm the environment. So all the existing triboelectric materials are made out of PP, PE, polystyrene, PET, and so on. Therefore, we were focusing only on polylactic acid, because pollution is less, and here impact on the human beings are very less. What you have done, so we are also working on 3D printing, but I keep 3D printing away from this presentation. So we have fabricated tank device for the touch sensor and the counterfeiting devices. So see here, this is the combustion synthesis of ZnFe2O4, which is very semiconducting materials. Or this is the procedure: adding metal nitrates and sugar and stirred with spatula and placed in a muffler furnace. It is a simple combustion process to synthesize nanoparticles. So at the end, you get ZnFe2O4 by this process after the calcination and crucible is taken out, and this nanoparticle is subjected to other characterization. And of course, once we have nanoparticles, we can fabricate nanocomposite while extrusion or by solvent casting. While extrusion is, of course, eco-friendly, but for the purpose of nano device, which is we need very small device. We have made a very small device. That's why we have opted solvent casting. The beaker, you can take chloroform. Polylactic acid is dissolved in chloroform, and then through ultrasonication, we have dispersed ZnFe2O4, then dried, poured onto the petri dish to get the film. Once the film is prepared, the film is attached to the aluminum tape so that it can capture the current. So tribal layer attached to substrate materials, and this is the fabricated device. You can see there's a hole, and when we tap, so you get different current. So this is to confirm the ZnFe2O4 XRD graph, which indicates the which confirms the what I can say, ZnFe2O4 nanoparticles shown in peak 17.72, 29.65, 34, 36, and so on. That corresponds to the plane of 111, 220, 311, 400, 422, 511, and so on. So these are the XRD patterns, demonstrate the different peaks for crystalline ZnFe2O4 phase, which are indexed in cubic structure. And the second one is IR structure, so which is ZnFe, which confirms OH, presence of OH as well as HOH, which is due to the moisture which is present in the ZnO4. And this is the XRD of PLA, so which is completely amorphous. And at the end, you get the 2 theta peak, which corresponds to the ZnFe2O4. That indicates the presence of ZnFe2O4 in the polylactic acid. Of course, it is not altering the crystallinity of the material, but of course, it is altering the texture, but not the crystallinity. You see here, this is the ZnFe2O4 nanoparticles, and the bottom figure indicates the same image of PLA, ZnFe2O4 filled nanocomposites. And the first graph indicates the voltage versus time. You see here, it is just PLA, and with 0.25 grams in PLA, 0.45, 0.65, and 0.85 percentage. Sorry, it is not gram. It is as the percentage of ZnFe2O4 increases up to 0.65, it gives a very high voltage of around 15 between 15 to 20 volts. But the moment you increase at 8.85 percentage, what is happening is, so the texture is damaging, thereby it is decreasing the voltage. So this is again the voltage versus time. So within a fraction of a second, we are able to generate a lot of voltage, which is very much essential for the sensor application. So the graph C indicates the output current versus time within 40 to 50 seconds, which can generate between 60 and 80. We have very high current. And the last graph, this is the output performance of the load resistance versus voltage. That indicates the material's performance behavior. And this is the circuit diagram for different material. And the first one indicates represents the circuit diagram for the change in the capacitor, the rectifier circuit altering the current material for the PLA and ZNF material, and which is correct. The capacitors with capacitance of 1, 2.2, 3.4, 4.7, and 47 and 100 microfarad, they can be charged to different seconds from 0.25 to 20 seconds. So the changing the capacitance by continuous tapping of 25 seconds. After that, calculator is connected. You can see here. So the whole current is stored in the capacitor charged, and you can see here within 25 seconds that stored amount of energy, which can give sufficient sufficient power to display in the calculator. The same amount of energy is used here, and you can see the 0 here, which indicates the power is generated in the capacitor. And this is the demonstration of glowing of LED lights using the tapping in the foot. So one of my researcher is tapping by foot the device, and he was able to generate the volts around within from 0. Within a fraction of a second, you were able to generate volts by jumping and stamping. So this is the demonstration of glowing of LED by the fabricated tank device. So using biodegradable polymers and some nanomaterial incorporated with nanomaterials, we were able to devise the device glowing. So this is just a demonstration. And this is blinking of LEDs for the touch sensor, you can see here. So this can be used in any kind of laboratories or any supermarkets where the people are moving. The people's movement, the moment if they touch the mat or anything, there will be a glowing of light that can be connected to the signal or arm, so that the people will know, okay, somebody is coming inside. So without any electrical power, with the board, our students were able to generate this kind of device, which can be used as a touch sensor. So the mechanism is very simple. So when you press the electricity, so they orient themselves. When you release, they connect to the positive and negative electrodes, and that collects the power, and that you can connect to the capacitors to store the energy. So you can tap it or stamp it. You can use it instantaneously for any sensor application, or you can store it for long. If the many people are storing, walking in some street, then you can use that energy, that electrodes you can place, the device you can place on the mat, and you can collect the power in a capacitor, or you can use it for any application. So other area we are working using nanocomposites is using these metal oxide nanocomposites. Here it does not involve any polymer so far. We would like to use some conducting polymer in the later part, but as of now we are focusing only on only on using metal oxide nanoparticles. So that is to detect the amlodipine bisylate in urine samples or any biological samples. Amlodipine, it's a calcium channel blocker used to treat high blood pressure and chest pain. Amlodipine works by relaxing blood vessels, improving blood flow, and reducing the workload on the heart. This is used for the BP patient. And we are used INS44 oxide nanocomposite on a modified electrode. Just we have pasted on the glossy carbon electrode is modified, and it was able to sense the amount of amlodipine bisylate in the material. So that we have detected using electrochemical sensor. So the synthesis is very simple. Just to make, so it is, it is a hydrothermal process. You use all the ingredients, zinc and indium and tetrastic acid, and everything is put together in a reactor and placed in an oven so that we get all the nanoparticles. So this is to confirm the nanoparticles, zinc oxide and zinc indium sulfate nanoparticles. And this is the transmittance which indicates which confirms the presence of composites. And this is the structure you can see here. This is the complete nanostructure. All the particles are in terms of 100 nanometers. And this is the XPS spectra in order to confirm the formation of the composite. And this is very important. You can see here current versus potential by varying this is the scan rate, okay, 0.1 millimolar to 1.1 millimolar. So as the concentration changes, the potential also changing. That indicates the material is, the composite is sensing the amlodipine bisylate. And when we plot against current versus concentration, we get a straight line, and the limit of detection is 0.0032 micromolar. Using the nanocomposite, we can detect this particular medicine, that is amlodipine bisylate, even as low, even at 0.0032 millimolar concentration. Yeah, this is with respect to pH. By varying the pH, we can also detect the materials at different potential. So next drug which we have used is the dopamine. Okay, as you know, dopamine, might we feel I have the right amount of dopamine, we might feel I have low dopamine level, because as and when the dopamine level increases in in human being, they feel very happy. When there is no dopamine, they feel very sad. So this is the structure of dopamine, which gives a lot of opportunity for us to do electrochemical sensing. Again, we have used different nanocomposite, that is bismuth, molybdenum, and calcium titanate metal oxides to detect the dopamine. So this is the synthetic methodology which we have adapted using, again, it is a metal precursor, stirring, and then hydrothermal reaction to get bismuth molybdenum oxide. And then we have used the same thing like bismuth molybdenum using calcium chloride, using hydrothermal reaction for the centrifugation, and ultimately we get the nanocomposite. And this is the structural elucidation of the nanocomposite in order to confirm the formation of nanocomposite. And this is mixing, and you can see here dopamine undergoes electrochemical oxidation as well as reaction by using 2 electron and also by 2 hydrogen atoms. And see, this again confirms the composite and individual bismuth and calcium oxides material. Yeah, this is the structure, because very important to have the structure. The structure plays an important role in detecting in electrochemical detection of any nanomaterials. Here you can see here the square shaped calcium titanate as well as bismuth nitrate material, which are very much important. The structure is very, very important to work as a sensor. So this is the cyclic voltammogram of the nanocomposite and glassy carbon electrode, and also the bare and glassy carbon. There is a difference, and you can see here the scan rate. As the scan rate increases, so as the concentration increases, there's a change in the current. And again, the concentration versus current, that gives, the plot gives limit of detection. And this is again linear. First one is scan rate from 10 to 100 microvolts. Again, when we change the scan rate, we are also able to change the potential. That gives a lot of wide range of opportunities for us to detect this dopamine samples in any material, which can be in urine or in the drug or wherever it is, or it is in the blood sample. So in conclusion, we were able to synthesize, we are able to fabricate both the nanocomposites which are used, which can be used for the energy harvesting and then sensing. We have also synthesized metal oxide nanocomposites for the detection of drug as well as dopamine. So the significant linear relationship was observed between dopamine concentration and excitation, particularly in the second one, when we are detecting dopamine using bismuth molybdenum oxides, we were able to detect the dopamine even in nanomolar concentration. That is largely because of the large surface area and the porosity of the nanocomposites. So all this work was carried out by my dear students, Karepagoda, Vishnu, Appu and Anusha. They are all my PhD students, and all the contributions and credit goes to my students for carrying out this wonderful part of the work. So I also thank all the organizers for giving me an opportunity to present what we are doing at Adichunchanagiri University in terms of nanocomposite. And we are basically a polymer scientist, group of polymer scientists working here. Slowly we are working on the metal oxides, nanocomposites, and also using them in a polymer matrix to create more and more miniature devices, because in polymer composites, whenever you want to make, you need a large scale machines and also large scale characterization. But this kind of this kind of research work gives a large scope in Indian scenario to have small setup and to do much better work. And Vijay Srivastava knows, in France, we had a very big workshop and very large machines, but we cannot have that kind of facility in India. We have to look around and see what best we can do within the available facility. So that's all from our side, and I will be very happy to take any kind of questions. Thank you very much for patience hearing.
Thank you so much, sir, for such an insightful and thought-provoking keynote. Your expertise and innovative perception have truly encouraged our understanding of this critical area in material science. Now we will move on to the question answer session. If you have any query, please type in the chat box. Professor will answer the question one by one.
Yes, there is a question.
Yes.
I can read it for you. So, Umamis, are you able to see the question? No.
No, I'm not able to see. I'm not able to see.
I'm also not able to see.
Okay. So in the context of additive manufacturing,
Yeah.
how do specific 3D printing parameters such as infill percentage and that influence the transition of the PLA TPU blends into shape memory polymers?
Yeah. Okay. So this is a very good question, actually. So the infill density plays an important role. But as you know, PLA is very rigid polymer and TPU is very flexible polymer. So what you are going to do, suppose the moment you mix polylactic acid in thermoplastic polyurethane TPU, so you are going to create a fiber structure of TPU in rigid PLA matrix. It is like polymer composite. You will have a fibrils of thermoplastic polyurethane and matrix of polylactic acid. So the moment you change the infill density, you are going to change the number of fibrils, TPU fibrils. So therefore, the moment you increase the density, the infill density, it will become more and more flexible. So in that way, I think in terms of characteristics, shape memory polymer, lower infill density is better to achieve more shape memory behavior. If you have more infill density, 100% infill density, then shape memory behavior will be very less. You can achieve maybe 80% with 80% infill density. If 100% infill density, you can achieve 100% shape recovery. What we can say, shape recovery.
Thank you, sir.
Yeah.
And I can see one more question. what challenges might arise in scaling this approach, such as incorporation of COFE2 for nanoparticles, enhance the triboelectric and biodegradable properties of nanocomposites for industrial applications?
Yeah, it's really challenging because if you want to scale it up, we need to have some reactor. The process is very simple. We need to do reactor, so control the size and shape of the nanoparticles. So once we have that, we can have, we can do melt extrusion process instead of solvent casting. We can do melt extrusion. You have large quantity of polymers, then film blowing, and you can use the same film for triboelectric application. Whatever we have done within our facility is the solvent casting, but that doesn't mean that melt casting can't be done. Melt casting is much easier than solvent casting actually, because you don't need chloroform or anything. You don't have to wait 2 days to solvent to operate. In melt mixing, it's very easy. Just you mix both polymer as well as nanoparticles, then extrude. Then you can do film blowing or calendering to get the film for triboelectric material.
Professor, I have a specific question. Like, for example, if you are doing the melt blending, you are using some Brabender mixer or something like that?
Yeah, twin screw extruder. Normally, twin screw extruder. Brabender can be used, but Brabender, again, it is just for mixing. You cannot have a filament or a granules. Again, you need to do granulation. So it is better to use twin screw extruder in a large quantity, extrude, take the granules, and then do film blowing or calendering. So then you get a film.
For example, after twin screw extrusion, you directly take the filament or you will remelt it?
Yeah. Again, you take the filament, cut it, make it into granules, use those granules in blowing.
Okay.
Yeah, we cannot do it directly because the mixing and blowing, it's very difficult to do simultaneously. But it's better to do it, in the second cycle because it's a thermoplastic polymer. It will not undergo any kind of degradation, which is well within the melting point. It is within the melting point or degradation temperature of the polylactic acid. The properties will not go down.
Okay.
Yeah.
Nice to hear from you. I think we can also try to collaborate some work.
Definitely. Yeah.
Thank you very much, Prashantha.
Yeah, sir. How are you, sir?
Now I'm happy to see you in India
Yeah.
because when I visited in France,
Yeah.
I advise you to move to India.
Yes.
You
You
remember
advised me to
my
shift
word?
back to India. Yes, I worked there for almost 16 years. 16
Yes.
Yes.
What about your daughter? Where is she?
Yeah, now she's in India. She's in 9th grade now.
Yes.
Yeah.
Now she.
So
Good.
nice to see you, sir.
Okay. I
IIT
will.
BHU. Yeah.
Whenever next year, the
Yeah.
8th series will be in IIT BHU
Okay, sir.
in December 2 to 4 December.
Okay.
So I will advise organizer to invite you.
Sure, definitely.